So you want to know how to do the friction part of the final project. Well, here is just one example that you can do. If you can figure out another way to do it, that's totally cool. You don't have to do this way. But this is just a really nice way to do it, because the problem with the friction part is you don't necessarily know what the applied force is. And that applied force is what's causing the acceleration anyways. So this is a way to really let us know what the applied force is. We haven't done a question exactly like this in class. We talked about it a little bit, but it's math that you can do. We just haven't done a question exactly like this. So how this works is this is essentially a multiple mass system, okay? So I've got my mass 1, which is just this briefcase thing. It's actually backgammon. I think we played backgammon. So it's this briefcase thing that's going to slide on the table, and I'm going to calculate the friction of this briefcase. This is my second mass, this water bottle. It's attached to a string, and it is going to hang off the side of the table like so. So that when I let go of the briefcase, the water bottle pulls it down as the mass accelerates, or as the water bottle falls. So that's how this system is going to work. Now, you don't actually need a pulley here. If you have a pulley or something round, like I could just take this marker, to be honest, and place this, tape it really, really tight along the edge of the table so it's something round. That will decrease the friction and make it a lot better. But you don't have to. You can literally just have string across here, go like that, boom, let it accelerate across the table. You can see even, right, the friction changes the way that the object slides every time. So if you can decrease the friction when you actually do your final build, I would strongly suggest that. So let's dissect this a little bit and let's figure out just how this works, okay? I'm going to do this question on the whiteboard because I miss using whiteboard sometimes. So what we have here is a table, like so. We could say that we have a pulley on the edge of the table, but it's not necessary. We have mass 1 on the top of the table, and it's connected to a string that goes around off the table and is hanging down from mass 2, okay? In this case, mass 1 being the briefcase and mass 2 being the water bottle that's hanging off the side of the table. So if we look at the free body diagrams here, okay, if we look at mass 1, okay, this is mass 1. Well, we have, this thing is going to accelerate that way, which means we are going to put to the right positive, okay? So if this is to the right, if that's positive, well, mass 2 is also going down. So this is a very key part of this type of question, is you have to be consistent with the two masses. If moving to the right, the system as it slides off the table is positive, then that means that down must also be positive for mass 2 because they have to be consistent. So if we look at the free body diagram here for mass 1, what we're going to get, I'm just going to move it over a little bit. Okay, we're going to get here mass 1. We've got friction pulling it back, and we have a tension in the rope that is moving it forward. Okay, which means we are going to get the sum of the forces is going to be tension minus the force of friction is going to equal mass 1 times acceleration. Okay, so there is our first formula from our first free body diagram. Our second free body diagram comes from mass 2. Mass 2, okay, there's M2, has the force of gravity going down. Remember, down is positive because we have to be consistent, and this tension pulling it up. So the sum of the forces in this direction is going to be the force of gravity minus tension, and that's going to equal mass 2 times acceleration. So we've got our second formula. The only problem, we don't know tension, but we can use this to get rid of tension. This is a system of equations, okay? So what we can do is I can say that from this equation, I can say that my tension is equal to the force of gravity, which I'm going to now write it as M2 times G, minus m2 times the acceleration. So I took my tension, I moved it over to the other side and brought my m2a over to this side. And now I'm gonna plug this into my first equation. So my first equation becomes m2g minus m2a minus the force of friction equals m1a. Okay, now this equation is where the magic happens. Okay, we got rid of the tension, so all you need to solve this, all you need is the acceleration and the masses. You need the masses and you need the acceleration. If you know what mass 1 and mass 2 is, and you can find the acceleration, maybe by measuring the distance that the thing slides across the table, right? You've done this before. So maybe you time how long it takes for this briefcase to move a distance across the table. Now you can calculate your acceleration using kinematics, and then you can go ahead and use this formula right here, right? You've got gravity, you've got your masses, acceleration, your force of friction, right? That has your coefficient of friction in it. So you can go ahead and solve it all the way, okay? I'm not gonna do the rest of the question for you because I wanna leave some of it up to you, but this right here is how you would do it, okay? 2 free body diagrams, one sideways, one up and down, okay? Getting your 2 equations, substituting in for the tensions, and you get there, okay? I am going to post a much better worked out solution to this on Nexus with like I'll do it on my iPad, so it looks a lot better than that. But this is just kind of a quick, brief introduction on how you would do the friction part of your final project.